Αγαπητοί φίλοι και φίλες, έχοντας ολοκληρώσει τα εισαγωγικά, μπαίνουμε στο καθ' αυτό μέρος της εκπομπής μας. Θα ακολουθήσουμε τη διαδικασία της υποβολής ερωτήσεων προς τον δόκτορα Κέιτσι, τις οποίες ερωτήσεις θα υποβάλει ο δόκτωρ Εμμανουήλ Αγγελάκης στα αγγλικά και θα τις βλέπετε εσείς υποτιτλισμένες στα ελληνικά από κάτω. Μετά από όλα αυτά θα παρακαλέσω τον Μανώλη να πάρει το λόγο.
Ευχαριστώ πάρα πολύ, Σπύρο. So, on the 21st of November, so end of the year that just turned, there was a press release from the European Southern Observatory that attracted the attention of all of us. And I'm reading from that publication of the ESO that for the first time we've succeeded in taking a zoomed-in image of a dying star in a galaxy outside our own Milky Way, which is already catching your surprise. And then later I'm reading that we discovered an egg-shaped cocoon closely surrounding the star. And finally, we are excited because this may be related to the drastic ejection of material from a dying star before a supernova explosion. So, Keiichi, first of all, I also wish to wholeheartedly welcome you to this show after not having you for so many years. And I think that tonight there is a lot to unpack. Already the first paragraph of the press release was absolutely attracting your attention, and there is a lot to unpack. So the first question that I would like to start with would be, what was exactly that made it to the news? What was exactly the discovery that pushed ESO to publish such a press release?
Well, first of all, as the title said, it was the first zoomed in or close-up image of an individual star outside our galaxy, out of Milky Way. And this is quite difficult, and it's first of all technically difficult because the star is actually quite big, much larger than the sun. But the distance, and then the star is not in our Milky Way galaxy, but in another galaxy called Large Magellanic Cloud, which you cannot see from Greece. Unfortunately, you have to go to the southern hemisphere, for example, in Chile, where I am. And anyway, so the distance to this neighboring galaxy, Large Magellanic Cloud, is some 160,000 light years. So the distance is so great that it's beyond the imagination. It's hard to imagine how great the distance is, 160,000 light years. But it's so far away, so then the star looks so small, and this is the challenge. And so that you can have some idea how small this star called WOHG64 looks like. I mean, this WOHG64, this star has no other fancy name like Betelgeuse or Antares. It's just the catalog name, unfortunately. And so that you can have an idea how small it looks. You can imagine that for example, so can you imagine? So this is the map of Europe. Do you see that?
Yes.
Yeah.
And then, for example, here
it is in Greek.
Yes, exactly. Yes. This is the Google map. This is the Google map, and then the Google map has a very nice function to change the language.
Yeah.
So this is the map of Europe, and Thessaloniki, where you are sitting, is here. And now, for example, here is Paris in France.
Right.
And in Paris, is Eiffel Tower. It's a very famous tower. Okay, and then
Yeah.
you can imagine that the a ping pong ball, a ball for ping pong,
Yes.
Yep.
uh, of this size, and you put a ping pong ball at the top of Eiffel's tower like this. Okay, it looks very big. It
Yeah.
looks like huge balloon, but you have to imagine that the what we really put on at the top of Eiffel's tower is just a real ping pong ball of this size. Okay, and now you are sitting in Thessaloniki, so we put a telescope and we observe this ping pong ball at the top of Eiffel Tower in Paris from Thessaloniki. And then and then you imagine then the ping pong ball looks super, super, super small. And the WHG 64 in the Large Magnetic Cloud looks as small as a ping pong ball at the top of Eiffel Tower, seen from Thessaloniki.
Oh.
This is breathtaking to realize the advancements of the technology that are necessary for such observations of what you just said. So we definitely got a very clear impression from all the things that you told us about the physical dimensions that are involved. Um,
Mhm.
one of the very first things, because I know to much extent the work that you have been doing when we were together in Bonn, and also the group that hosted you from Professor Weigel here in Bonn. I have actually one of the first things I thought when I read the press release was whether this has been an accidental discovery from your side, or whether this was actually something that you were after. And if this was something that you were after, how would it have been chosen, etc., etc. So share some thoughts and share some insights with us on this.
Yes, so the actually the WOGG 64, although the name is very uh, although it has no fancy name, its proper name, but it's a very extreme object in a sense that it is ejecting its material at such a tremendous rate. And it is a dying heavyweight star. And therefore, it is one of the brightest stars in the large magnetic cloud if we observe in infrared light. And I will show the
Is it correct to say that if you bring this star in the place of our sun, then it will
yeah.
occupy a part
Mhm.
of our solar system up to
Yes,
Saturn?
yes. I will
Oh,
show this. I will show this. All right. So to have an idea how big the star is, okay, I said the star looks as small as a ping pong ball on the top of the Eiffel Tower, seen from Thessaloniki. But the real, so it only looks small. The real size of the star, WHT 64, is huge. So this is a very schematic, uh, say, picture of a solar system. Here at the center, there is a very small orange dot, which is the sun. And this very small circle is the orbit of the Earth. And then this one is the orbit of the orbit of Saturn, and this is the orbit of Neptune. So basically, this is the Neptune is the outermost planet of the solar system because Pluto is not a planet anymore. So if we put the as Spiro said, if we put WG 64 in at the place of the sun, it looks like this.
oh,
So it's quite big.
So we definitely get an
Um,
impression of the size of the
right.
star in reality. Yeah.
Yes. And now let's go back to the question of Manolis. So
Mhm.
the WGG 64 is a really huge giant star, dying heavyweight star. and ejecting material at such a tremendous rate, and it's very bright. So although the distance is quite great, if the object is bright, it's easier to observe. And then it's such an extreme, unique object that is ejecting, losing its material extremely. So that's why this star has been catching our attention. And actually, this is not the first time for us to observe this star WTG64 at high resolving power. Back in 2005 and 2007, we observed this star with the same facility at European Southern Observatory in northern Chile. And at that time, we already measured the size of the star. But at that time, we didn't have an image, but only this the measurement of the size. I mean, how big the star looks, right? And then, because we didn't have an image, we used the data, and then we made a computer model. And then the computer model said, well, the star is not just surrounded by, say, round shell, but it has a big donut. I will show this. So again, this is not an image we took at that time, and then it was the image artist impression. Made when we made the press release from the European Southern Observatory. So here at the center, there is a star, and this star is the gigantic star which fills up to the orbit of Saturn. Okay, and then surrounded, this is already the size of this white spot. This is already the size of Saturn. And then surrounded with a huge donut. And this is what our computer model said based on the data. But at this time, the European Southern Observatory had the first generation instrument of the so-called Very Large Telescope Interferometer, some special facility infrastructure to do to close up or zoomed in observations. We could measure the size, but not the image. And so actually, we were waiting for the next generation, second generation instrument that enable us to take a real image and to see if our computer model is correct or not.
Okay. Let me try to wrap up for the general public. So in 2005, 2007, already using techniques, the interferometric techniques like you use today, you could get a constraint of the size. That means you could get a sense of how big the star is. And then understanding a little bit the physics and understanding a little bit the dynamics of the environment, the picture that you just showed us is what it should look like for these constraints of size and for these physical processes in the close vicinity of the star. I suspect that during our discussion tonight, later we're gonna at some point say that, well, this was the artistic impression according to the measurements that the poor, if I can say, measurements that we had in 2005, which have been confirmed with a much higher resolution, and the image that you got at the end of 2004 that was published recently, confirming this artist's impression, if you like. Good. So the answer to my question is obviously that was not an accidental observation. It was not something that, for example, it became bright, it attracted the attention, etc. It was something that has been targeted, has been followed for the several past decades or so, or a couple of decades. And this observation is a result of a persistent, systematic attempt to learn something about this really, truly exotic environment, such as a giant star out of different galaxy. So I, from my professional standpoint, I suspect a number of reasons why such systems are interesting, and I'm sure that there are even many more. So my question is, do we have such close images of stars in our own galaxy or in other not in other galaxies? This is the first time. Other
Mhm.
in our own galaxy at least.
Yes, I would say the astronomers have taken close-up images of the surface of stars other than the sun, like 20 or a little more than 20 stars. Thanks to the advance of the technique to get high resolving power or zoomed in images.
Mhm.
And maybe I should show an example.
Yes.
For example, this one. So this is a very nice astrophotography, Milky Way, and this is one of the VLTI telescopes here. And then this is the constellation Scorpion. This is the head, and this is the tail of the Scorpion. And this bright star is received the very gigantic star called Antares. You can see that this star you can see it from Greece if the
Yes.
night is dark enough. And then it was 2017, we published the image of the surface of Antares with the best resolving power or the best close-up image, which looked like this. And so this is the surface of this gigantic star Antares, and you can see some bright spot or bright regions, and this fluffy thing is the atmosphere of this star. And this is one of the image, and then the images like this, maybe a little say the little lower resolving power or less close-up images, but then we have about 20 or a little more than 20 images of stars other than the sun.
Okay, good. Do you want to spare a few words about the technique and the specific arrangement of the observing apparatus that you use for these observations, Keiichi? Because yeah, I know, but I think it's interesting for everyone to learn how challenging, how difficult, how precise this instrumentation is, how expensive because of all these reasons. So, do you want to share a few about what is actually the specific apparatus that you use for the telescope, the facility that
Mhm.
was, and what is the novel technique that is utilizing such high and high resolution images, so that would be the equivalent of seeing a ball on the top of the Eiffel Tower from the satellite.
Yeah. Okay. So to have such a high zoom in power, we need the very big telescope, because the bigger the telescope is, or basically the telescope means mirror. Bigger the telescope is, the better or the higher the sharpness, or the sharper is the image, or the higher the resolving power, or the zooming power. Okay, so now, for example, to take an image of this star WG64 in another galaxy, uh, or the ping pong ball at the top of Eiffel Tower, seen from Thessaloniki, we'll need a telescope larger than 100 meters. It means we'll need a mirror larger than 100 meters, its diameter. And to make such a gigantic telescope with a 100-meter mirror or more than that will be very, well, first of all, it doesn't exist. And to construct such a gigantic telescope with a 100-meter diameter mirror will be very difficult and very expensive. So instead of constructing such a gigantic mirror, we combined 4 telescopes. And then each telescope is not so big, just 1.8 meter in diameter. But if we combine the light collected from 4 telescopes and process it in a proper way, in a special way called interferometry, then we can get a resolving power or zooming power equivalent to the separation of the telescopes. So I will show the facility I used.
That would be very helpful. Many of Spiro's show observers, viewers are observers themselves. They will very follow what you're saying.
So this is the aerial view of the Paranal Observatory of the European Southern Observatory, which is in the northern Chile.
Mm-hmm.
It's about a little more than 1,000 kilometers from the capital, Santiago. Now you can see some telescope for 8-meter telescopes, and this is another telescope. Now, another aerial view is like this. So they have here 4 8-meter telescope. You can not see the mirror, but you can see the domes. And then there are 4 small telescopes here, 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 and here. And then we combine the light collected by those 4 telescopes and process in a special way. Then, in that case, for example, we can have a virtual patched-up telescope of this size. Each telescope is small, just 1.8 meters. But if we combine them, if they work them together in a special way, then you can imagine that we have a telescope as big as this.
Are they movable?
Yes.
The little
I will
ones.
show. Yes, I will show you. And then in this case, for example, the separation from here to here is like a little more than 100 meters. In this way, we can have a virtual patched-up 100-meter telescope, and this is exactly what we need to have the zoom-in power to get an image of WHG64. And these 4 big telescopes fixed, of course, but these 4 small telescopes can be relocated, okay, like this.
Huh.
So what they do is they jerk up a telescope, and then there are, maybe you can see that here, there are rails, like train. And then along the rail, for example, this telescope is jerked up, and then along the rail, it's move to a different location, as you can see here.
Wow.
So in this way, we can have a virtual 130-meter telescope. And in our case, the largest separation was 130 meters. So that's why we had a virtual 130-meter telescope, and that gave us the resolving power, the zooming power.
Necessary for resolving such a distant object. Of course,
exactly.
The interferometer is equivalent with a 100-meter telescope or so in terms of resolving power.
Yes.
For sensitivity, of course, one would need a larger collecting area, but that's just a technical detail which I mentioned only.
Yes.
For
yes. So this is at that when we observed WGG64 back in 2005 and 2007, they could combine only 2 telescopes. We used the instrument that combined only 2 telescopes, and that's why we couldn't make an image. Now we use the second generation instrument called Gravity, which combines 4 telescopes. And that is the key to make an image. And also, as Manolis touched, it's the star is not bright. Okay, this is the brightest star in the infrared light in the Large Magnetic Cloud, but still it looks so weak. So therefore, well, you can again the comparison to the ping pong ball in France. Okay, ping pong ball at the top of Eiffel Tower, seen from Thessaloniki. But now you have to imagine that it's at night, dark, and this ping pong ball on Eiffel Tower is only really, really weakly illuminated. It's not the light. It's not emitting strong light like a lighthouse, but only maybe like a candle, very, very weak. And you want to see it from Thessaloniki and take a photo. This is a challenge.
This
And
is
the
truly challenging.
yes, and then the second generation instrument gravity is exactly the instrument that make it possible.
Well, let me take the opportunity to ask a question here. Because also, I am an observer by training, and I know how hard it is. I wonder what was the most challenging data pre-processing step that you had to take, because I assume that every source of noise, because especially because you have been observing in the infrared band of the spectrum, every source of noise must have been extremely challenged to overcome. So what was a major difficulty you had to bring the data to a quality which would be good enough
Yeah,
to science?
yes. So the point is with this technique called interferometry, we do not shoot a direct image like this,
Yeah.
but we measure some data, and then later we process the data and reconstruct or restore the original image. And this restoration process is the complicated thing. And I guess the greatest challenge for me was to check and to be sure if we see what we see in the restored image is really true, or maybe just say just some
An artifact of
errors.
the technique. Yeah.
Yeah, artifacts, not real things, simply coming from or the resulting from some problem in the data processing or in the restoration process. And so in the end, I will show this image that we obtained.
Yes. And we will
Uh,
need that to focus a little bit on
yeah.
this anyhow.
Yes. Oh, so maybe I will start this, and this is because maybe the audience in Greece might not have seen the large magnetic cloud. Well, you have to, even in Chile, you have to go to places with dark sky. In Santiago, where I cannot see it. So this is the large magnetic cloud. It looks like, with the naked eye, it looks like a very diffuse cloud. So that's why it's called large magnetic cloud. And this is the small magnetic cloud. And this is the large magnetic cloud, but seen in infrared light. And this is our star, WHG 64.
Mm-hmm.
And this is the image from the press release. And
Mm-hmm.
in the end, guys, what we see is this thing, like an egg,
Mm-hmm.
and this ring, a larger ring. And in the end, we are sure that this egg is real.
So
It's
are you
not
saying
the
that the
yes,
surrounding rings, the donut-like shape, is
yes.
an artifact of the technique?
We cannot exclude that possibility, but
Okay.
we probably real. And to confirm this ring is really real,
Mm-hmm.
we need more data.
Right.
So
What was the volume of the data you processed in order to get this?
not so much. I don't remember how many gigabytes it was, but the
Mhm.
original data of the size of I don't know, maybe 10, 20 gigabytes. And
Mhm.
then after the data processing, it goes very, very small.
Yeah.
And then for the restoration, and then the image restoration process is done with the reduced data, not the 10 or 20 gigabytes data. So the data side is not a problem.
Mhm.
Mm-hmm.
Okay.
Keiji, how many observing hours did you need for this, and over what period of how many days was it spread?
2 nights.
2 nights only.
It's 2 nights, but full nights,
Okay.
because I will show this again. This the observatory, and on one night we had a telescope configuration or telescope positions very wide. I mean, this means the first night the telescopes were located wide apart, maybe like this. Not exactly like this, but the separations were quite large
Mm-hmm.
on one night. And then several nights later, maybe or 1 week later, we observed the same star during a full night. But then the telescope configuration was much smaller. This means the telescopes were positioned like here, another one here, here, and here. So very compact
Yes.
configuration. So this was necessary to have a reliable restoration process of the image.
So I assume for our viewers that in the first night you use an expanded configuration so that you could get the fine details, and then you brought the telescopes together in a compact configuration, which of course would also result in much lower angular resolution. So the resolving power would be much smaller, but it would also be able then in that configuration to detect more diffuse regions of emission. Is that the reason?
Exactly.
Yeah.
Exactly. Yes.
And then you
Because
combine
the
the two to get a more complete image of reality.
exactly, yes, exactly. So because the before our observation, we didn't know so much about the object, what the object looks like. Well, we had a computer model, but which might have been wrong, completely wrong. So the as Manoli said, we wanted to have this very wide configuration, very large configuration of the telescope to see details, to capture details, and the also very compact configuration to see something uh, diffuse, because we didn't know that.
So in a sense, this is even more impressive now that we talk and we start to unpack all this. This is even more impressive, the whole story, because you realize that you are going after something for which you have very high uncertainty of what you're going to find, because all you have in your hands is an estimate of the size and a computer model that tells you how it will look, but you have no certainty at all. And given the very low power of the source itself and how dim it is and how far it is, and also that it's dynamic, so it may have changed since 2007 when the simulations were, you really are very uncertain about what you're going to find. But in the end of the day, with only 2 nights of observations, you got a smashing result. This is really, I mean, it's really an impressive result on its own sake. So I wanted to take this a bit further. If we focus on the image that you managed to acquire, um, having in mind, let's say, what we can understand for this system, for this environment, for this uh, cosmic environment, if you like, what is that you should ask an unexperienced spectator like us, that we are viewing the show tonight, to pay attention in the image? So, what is, in your opinion, as a professional astrophysicist, very deep into the system, the features that we see in the image that can tell us something about the physics and the processes that they take place there?
Mhm. Okay, so then I will show this image again. So the egg, this egg-shaped cocoon,
Mm-hmm.
and the so the I think this is the we think this is material ejected from the star, because the star itself, although it fills up to the orbit of Saturn, it's very small in this image. So it probably it is hidden in the cocoon at the center. but we don't see it. And what we see what I want the audience to understand that this cocoon, this egg-shaped cocoon, is not the star. It's not it's not a star like a rugby ball, but it's just a material ejected from the star. And what's important is it doesn't look like a donut. Okay, maybe this ring can be the rim of the donut hole. So I will show maybe I will explain better with the camera. So
did you pause?
this is donut.
Yes.
And we thought
Bon
the star
appetit.
center, the center star is here, and then we are seeing like this star and like this. Okay, and then this is our computer model set based on our previous measurement data, and this was depicted in the artist's impression in ESO press release from 2008. Okay, and what I want to say is this part of donut. Okay, this part of donut, and then we have the star here. We have a star, and then the star, of course, emits the light. So this part of the donut hole is heated by the star directly, because this part of the donut hole receives the starlight directly. It's heated up, and it emits infrared light. And this is what we see in as the ring. Okay, so why don't we see the rest of donut? Because the rest of the donut is too cool to emit this infrared light.
All right.
So now, but then our donut model did not predict this egg-shaped cocoon. Let me put the donut away. And okay, so then we thought, we think this is the material from the star, ejected from the star, but not predicted by our previous donut model. And then what is wrong? Maybe our donut model was completely wrong. And then we found out that we looked up some data, because this star is quite famous. So there are some the measurement of the brightness. So measure the brightness is much easier than taking an image. So there are many measurements of the brightness, and we found that the star has become much fainter than before, than the one when we observed the star for the first time back in 2005 and 2007. So that's why the thing is, in the meantime, in the last decade, probably the star has changed, has been evolving somehow. And then at some point, we think the star started to eject more material. And this this egg-shaped cocoon is the consequence of this ejection of material, more higher ejection of material. And so this is the case, not just the image, but also the evolution in the last decade is one of the discoveries.
So, in fact, from what you're saying, and that's also very clearly communicated in the press release and in the publication that you made, is that the system is dynamic. So, this is another thing that later we're gonna also emphasize a bit more, is that not only is that a dying star, not only is that a direct image of a dying star in another galaxy, but it's one of the very few cosmic phenomena and systems that not even in a lifetime's period we can observe its evolution even shorter than that. So within a decade, we see the thing changing, which shows already how dynamic it is. Just to cast a misunderstanding, KG, the image that we are seeing is not real color. It's a fake color, obviously, right?
That's right. Yes, yes. So this is we observe infrared light,
Yes.
and just to understand, I don't know if I guess many people have heard of infrared light, but what is good for? And to make this point, I prepared a slide
Yeah.
here. This one. Okay. So this is a guy with his hands in a black plastic bag, and this is normal photo, normal image. With it, this means a photo taken in light that we see. It's called visible light. Now we shoot the same object, this man and this man, in infrared light.
Mhm.
It looks like this.
Oh,
We can
Thermoplastic.
see his we can see his hands in the plastic bag. Now we cannot see his eye, but just glasses, dark like sunglasses. But obviously, he doesn't have sunglasses on, just normal glasses. So the thing is, it's thermography. Maybe some people have heard of thermography. This means with thermography, we can measure the infrared light emitted from warm things. Therefore, for example, here, his face is warm, so it looks very bright in infrared light. But here, why glasses look dark? Because the glasses blocks the heat from his eyes. That's why it looks dark. And then in the infrared light, you can see through this black plastic bag and see the hands because his hands are warm and emit infrared light. So the point is, if we observe, for example, stars or galaxies in infrared light, we can see and we can investigate different things. Or we can, for example, see through some material blocking the usual visible light. And
Yeah.
the infrared light we cannot see with our eyes. Therefore, the image we took is in infrared light. So basically, we cannot put any color. But then why this color? Because it looks warm. It can be blue or it can be violet,
yeah.
as you like,
Yeah.
or it can be rainbow. It's a matter of taste.
It's always so impressive to see in reality how different perception of the universe one gets just observing at a different wavelength. And now we're talking about infrared, which is not that different from the usual wavelengths that our eyes are using. So it's are detecting. So it's really impressive to see how different the impression you can have is. One thing that you implied, you didn't specifically say that, but I would like some clarification into that. Is it, did I understand correctly that you have an impression or an estimate of the inclination of the whole structure towards the observer? And if that is the case, how has that been achieved? Or was that a misunderstanding from my side?
And at the moment, no, because the if we okay, so let's go back
I
to
asked
this
that because
image.
you showed the donut
Yeah,
and you
yeah,
implied that
yeah,
it's a little bit inclined towards us.
yeah,
But I
yeah,
guess
yes,
one answer would be that you judge that from the geometry that you see. Or
yes. So so if we think if this ring is really real, not artifact or error from restoration process, then we can. Okay, I will take a donut again. We can see, of course, we are not seeing the donuts like this, probably like this from you. And
Mhm.
then you can see then the donuts, basically donut is circular like a ring, but then it looks like a bit compressed.
yes, yes.
And with this, you can estimate the angle.
Mm-hmm.
But I guess we should do that once we are sure that this ring is real. And
Uh,
now, yes,
uh, I want to ask you why egg-shaped and not spherical?
yes, it's a good question, and this is exactly what I wanted to say. And now this egg is not round because the star itself should be more or less round, but it's it's like this egg shaped, and we think it is because of unseen companion star inside the cocoon. So
Oh,
Wow.
the what we think is two scenarios. This is also related to the angle, the viewing angle that Manolis mentioned. So in one, no, like in one of the hypotheses, uh, again, I need a donut, and then egg can be like this. So this is okay. It's not. It's a pencil. It's not an egg. But then you have to understand this part of is like the egg-shaped cocoon, long cocoon, and then it is like this, and then you see it like this.
Mm-hmm.
So this is the egg-shaped cocoon, right? So well, then you can see the donut, and then inside something long. Okay,
Yes.
this is one hypothesis. And
Mm-hmm.
then in that case, or this is even more difficult. So the other, sorry, donut has so much sugar. So the okay, so we have donut like this, and then inside donut, maybe there is the this egg-shaped cocoon is like this. But in this case, in the first case, the cocoon was like this, perpendicular. This is donut, and then the cocoon was like this in the first hypothesis. Now in the second hypothesis, cocoon is like this. Again, well, we can see the same thing. If the donuts is like this, is and the cocoon is in the plane of donut, and then you can see like this, and then basically you have the same appearance.
Mm-hmm.
And in both cases, we think the unseen, this star has an unseen companion star, and then the interaction between two stars can make the spherical round things to egg-shaped cocoon. So in the first scenario, maybe because of interaction, material is ejected only in this direction and in this direction, in the direction of the North Pole and from the South Pole. In the second case, maybe we have the gigantic star and its unseen companion, and then because of interaction, this round cocoon is deformed like this
It's
because this
elongated.
the companion is here. The companion star is here, but we at the moment we cannot distinguish two scenarios.
Yeah. Yes. And I was thinking that a very typical question in second year astrophysics in the physics department in Greece, a very typical problem that is given is whether you would be able to see, for example, from a very far distance, whether you could discriminate Jupiter and the Sun. And the long story cut short is that, of course, if you're observing visual light, where you have a star or sun dominating the sky, you won't see anything else because you're
Mhm.
about to be overshined. But if you were shifting your observing band pass towards the infrared, where the Jupiter this time is dominating because our sun is very, very hot and the Jupiter is much colder, the Jupiter would dominate and you would actually be able to resolve it. So if this scenario, if if you were after answering the scenario of a companion star, would such an observation help you?
Yes,
Probably.
the different observing at different wavelengths.
Exactly.
Yes. So as I said, oh well, actually we wanted to, the thing is we wanted to observe this star WTG64 at longer wavelengths. There's this infrared light, but
Mhm.
the another type of infrared light. So the infrared light more sensitive to colder material to see the entire donut, not just this the only the donut hole, but the entire donut. And then it was not possible. It was unsuccessful. I mean, the first year they after this observation, we observed that, and then it was successful. And then but we had bad weather, so we went back. We submitted a proposal, approved again, and then we observed. We wanted to observe, but then it was unsuccessful because it had become too faint. Oh, that and then I thought, okay, the star is changing, and then we started to monitor the brightness without taking an image, just to monitor and measure the brightness every month. And then so far, the star is getting fainter and fainter. And maybe I can show you the example of the data. So this is WGG64.
Mhm.
And this was the image taken in October 2023, so more than a year ago. And then this
Oh.
is the image taken in December last year, 2024. So this is October 2023, December 2024. So this star, for example, this star hasn't changed its brightness, but obviously WTG64 here has
That's
become
true. Oh,
fainter.
yes.
This now. So the star is getting fainter and fainter, and therefore, because I think the material in the cocoon ejected from the star and the material in the cocoon is blocking the starlight. It's
Aha.
not that the star is disappearing; the star is still there. So maybe I will go back to the image.
That makes it even more interesting. Yet another
Yeah.
dimension
So okay.
complexity.
So this is the image in visible light.
Yeah.
It's fainter, but then it's not, the star is not disappearing, because if we take an image in infrared light, it's very bright, still there. So the star is not disappearing. It's just that it appears to be fainter because I think the material in the cocoon is more material is blocking the starlight.
Mm-hmm.
So then we can take advantage of this natural, say, sunglass, and for example, we it might be interesting to observe the target in ultraviolet light,
Mm-hmm.
because if we go to infrared light, the star is bright, as we showed, as we have seen. The star is getting fainter and fainter in visible light, but still very bright in infrared. So if you, as far as you are observing this object in infrared light, you only see the basically the bright star, not
Mm-hmm.
its companion.
Mm-hmm.
But if you go to blue light or ultraviolet light, there the star is very faint,
Yeah.
intrinsically faint, and now thanks to this the blocking of the material, blocking due to the material, it appears to be even fainter.
Mm-hmm.
And then if the companion star is a hot star, maybe the this companion star can outshine the red supergiant star.
Yeah.
and we can see this.
Okay, this is really very interesting. This is exciting, more than interesting. And I'm gonna pick up on the supergiant terminology that you use, but I'm gonna put a pause. I can't help asking you a couple of questions. Spiros knows that very well how obsessed I am with understanding or getting a sense of the physical conditions at the cosmic environments. So I have two questions which I have not planned, but they came naturally. Um, we have been saying that generally because by definition you have been able to observe in the infrared light because the material is generally colder. So first of all, I would like to have a sense of the temperatures that we are talking about this material.
Mhm.
We say colder, but in astrophysics, cold can have a very different meaning.
Okay, so first of all, the temperature of the star, the surface temperature of the star. This is the star, the gigantic star that fills up to the orbit of Saturn. This is
Mhm,
about 3,000 to a bit around 3,000 degrees.
mhm.
And I know this is really hot for us, for humans, but in astronomy they are called cool stars.
Yeah.
So
Compared
3,000
Good.
to 6,000 degrees
exactly.
between
So
the surface of
in,
our sun.
Yeah.
yeah, exactly. So sun, and then there are say hotter stars than the sun. So
Yes.
this star with the surface temperature of 3,000 degrees, it is a cool star.
Okay. So
Now
that's yeah.
the cocoon is the material in the cocoon is a little far away from the star. So therefore, I guess their temperature is like 1,000 degrees
Much lower.
lower,
Um,
but still hot.
and of
Yeah.
course, and then it takes me, but you won't necessarily feel that hot because of other reasons. So that it takes me to the next question that I had not planned, but I can't help asking, which is the composition and how would you feel if you could touch the surrounding, the dust,
Mhm.
especially that you said. You mentioned very
Mhm.
often the dust, which is one of the materials that form this embracing structure. So,
Mhm.
what is the dust made of? What is this material made of?
Yes, so in astronomy, dust is not just a house dust, but basically, you can imagine it's like a sand grains,
Ah,
sand
Yes.
yes.
grains, but much smaller. You can see the sand grains, but
Mhm.
usually the grains around in the universe can be much smaller, like smaller than 1 micron. 1 micron is 10,000 is 1,000 times smaller than 1 millimeter. So very fine sand grains, or in other stars, not WGG 64, in other stars, it can be soot, like a black smoke. It's a very black carbon grains.
Mm-hmm.
And this kind of material, or it can be like crystals. But
Mm-hmm.
again, crystals are different minerals, but then again, they are much smaller than, for example, than a crystal that we usually see on the Earth.
So, as a matter of fact, the terminology dust is not that far from what we intuitively understand when we hear the word dust. Good.
Yeah.
So now let me change completely the quality of the questions and move on to something that will help us a little bit understand the physics of this exotic system itself. You mentioned repeatedly the terminology supergiant. So, this is one of the different possible final stages of evolution of a star, which depends on whatever parameters they have. So tell us a little bit, Keiichi, if you like, a little bit about the supergiant. What is the characteristic? And then
Mhm.
I will read something from the press release, which has a lot. Please. So I'm reading. Let me do that first, actually. So I'm reading from Professor Weigelt when he was interviewed by the um, press release journalist. We have found that the star has been experiencing a significant change in the last 10 years, which you told us again and again in the most descriptive fashion. And he continues, providing us with a rare opportunity to witness a star's life in real time. We also said that in 10 years, in just a part of your own career, you have seen the star actually significantly changing. And then he continues, in their final stages, those stars, the red supergiants, like the one that you have observed, the outer layers of gas and dust in the process are ejected in a process that can be last thousands of years. This star is one of the most extreme of its kind, and any drastic change may bring it closer to an explosive end. Now, all this is full of excitement, right? So, tell us a little bit about the supergiant, the explosive end that it may have, when it's going to end it, what will be the evolution path to be expected?
Mhm. Okay, so it's about the stars, 8 or 9 heavier than sun, but more than 8 or 9 times heavier than the sun. And then at the end of their life, they enter the so-called red supergiant. So why is red and what is supergiant? First of all, the star expands. So the star is really blown up. It's really bloated
So it's
like
becoming
this.
a
And then
giant,
this is yeah. So then the not giant but super giant
supergiant.
because right at the same time the surface temperature cools down goes down. At the beginning, maybe it was like the more than 10,000 degrees or maybe 20,000 degrees, and now when they enter the supergiant stage, they expand, and then the consequence is the surface temperature goes down to 3,000 degrees. Okay, it's still hot, but much cooler than the 10 or 20,000 degrees. So that's why it's called red supergiant. And basically, those bloated cool stars are in the final stage of their life. And then it is we astronomers think after a while, at some point, they explode. Explosion means all the material, all the stellar material is somehow kicked out, like in an explosion like this. And actually, that happened back in 1987 in the Large Magellanic Cloud. And I have an image. So I think this is the so far the one of the most famous supernovae, supernovae SN 1987A.
Mhm.
So it is one of the okay. So it is in the same large magnetic cloud as WGG 64, but a different star. Okay, here there was a star, and one day in February 1987, it exploded. And the supernova explosion, when a star explodes in a supernova explosion, it becomes much, much brighter. I'd say 100 times brighter than the original star within a day or so. And it can outshine, it can be the single supernova can be as bright as or maybe brighter than the entire galaxy. And then over a year or so, it becomes fainter and fainter and fainter. So this is the supernova. And this is the end. This is the end of a star.
Mm-hmm.
So the death of the star.
Okay. Mm-hmm. What are the processes on the surface of those dying stars that can last thousands of years?
Yeah. So this is yes, in the red supergiant stage, the star is, say, ejecting the material. Okay, but okay, you can imagine that the star blows up like this, and then this is, say, so, but then this means this material, the star, is very, the outer layers are very fluffy. Density is very low and then very tenuous.
Mm-hmm.
Still, you have to think, at the center there is a star. In the case of WTG 64, 25 uh, 25 times heavier than the sun. So in principle, the gravity of this star 25 times heavier than the sun keeps the material. Nevertheless, keeps the material from flying away. But nevertheless, astronomers know that red supergiants are ejecting material. This means the material in this fluffy outer part of the star somehow manages to escape the gravity of the star and go back to the interstellar space.
Mm-hmm.
We know this phenomenon, we just don't know how it occurs. How the material, this tenuous material, manages to escape the star, because something must be pushing, some force must be given a push to the material so that it can go away. But we astronomers still don't know exactly what the force is.
So even if you don't know exactly the mechanism that empowers this
Mhm.
evolution, do we at least have an experience or an estimate of how fast it's happening? So if again, in human terms, would we be able to see this evolving? And if yes, how fast would it be evolving?
And it's a good question. The usually it's like 1,000 years, maybe 10,000 years. So
Mm-hmm.
in that case, the time scale is much longer than human time scale.
Mm-hmm.
But recently, the astronomers working on supernovae found out because those people are working on supernovae, but now they found out the stars before the explosion. These are the supergiant stars before the explosion were ejecting material such a tremendous rate, and some say it was like 10 or few years or 10 years just before the explosion.
Okay.
So this means well, it depends on who you ask. But some say just a few years before the explosion. Some say maybe some 10 years before the explosion, or maybe 100 years before explosion. But in any case, it's a human time scale.
Okay. So
And in this case, well, we might be able to see something in real time.
okay. So with all this, one understands that there may be an estimate of when this particular star is going to explode. And right? So what do you think? I guess you do have some estimates of when it's going to explode.
No, unfortunately not. Well, I
Okay.
would only say maybe in the next several thousand years, or within 10,000 years.
Okay.
Okay, so if I give a large number, it's safer.
Okay. So no chance that one of us will observe it.
Yeah, well, we don't know, because the point is we know that those heavyweight stars explode at the end.
Yeah.
But astronomers have not yet understood what triggers the explosion.
Mm-hmm.
So it's hard to predict.
Mm-hmm. Now, another thing that I've been thinking since I read the press release from the beginning was the following. We know that the evolution of the stars is not independent of the environments that they are living, and vice versa. We know that the life evolution that the different stars take influence the life of the stars in the vicinity. So my question is the fact that this particular system is actually living on the Magellanic Cloud, whether that has something to do with its evolution, if you have any such evidences that the evolution is triggered or somehow related to the environment it's found.
I don't think so.
Mhm.
Because this star WG64 is not in an area very crowded with stars.
Mhm.
So as you said, the stars in a very crowded area like a cluster, yeah, then interaction with other stars can influence.
Mhm.
But I think WGG64 is still living in relative solitude, maybe with a companion,
Yeah.
unseen companion. So therefore, the interaction with other stars is probably not so important
Well,
for the evolution.
in any case, the suspected or the alleged possibility that there is a companion star will demand an extremely dense environment to have any impact on the star, because the companion star, if it exists, will already have such a much more important gravitational impact on the system than the environment, that the environment could only make a difference if it was very compact after all, right?
Yeah.
Um, then that brings me to the final urgent, at least, question that I had planned for tonight's discussion, and that's what is going to be left after the explosion that this star is going to undergo in several thousand years.
Yeah, so probably only the core of the original star.
Mm-hmm.
And then the but the core, but the very compressed, very to extreme high density and with extreme strong gravity. And one is called the neutron stars, a star consisting of made of pure neutrons. Very compact and dense and high gravity, or it can be a black hole.
And that all depends, of course, on the material which is available, or majorly on that.
Yes, so basically the mass, how heavy the star is, and or maybe how heavy the star will be at the time of explosion.
Yes. This is all very exciting. I couldn't have wished for any better discussion, Spiros, tonight with Keiichi, that he took so much of his time to prepare for tonight's discussion. While just a few days from his summer holidays, because he's in the South Hemisphere. So I thank you very much, Keiichi, for this. Again, I congratulate you
Welcome.
for this achievement. This is groundbreaking. And thank you very much for
Thank you very
taking the
much.
time to talk with us.
Thank you very much for inviting me to this webinar. It's
Yeah.
a very nice and opportunity for me too.
Spiros, the microphone
It
is
was,
back at
it
you.
was, it was our pleasure to have you here. And Ohayo gozaimasu.
So I should have learned something in Greek.
No. Do you speak any Spanish already, Keiichi? I guess.
Yeah, Spanish. Yeah, I do because I have to give lectures in Spanish.
Oh, you
Oh.
teach in Spanish. Wow.
Yes, that's right. And then supervision of undergrad students, all in Spanish,
Okay.
and of course administration people in Spanish. So,
Yeah. Excellent. Thank you so very much.
but not Greek. Unfortunately, not Greek.
Next
not
time.
Greek. Yeah. Well, you didn't
Thank
have
you.
many Greek students even in the group when you were in Bonn. So
Yeah.
good.
Thank you.
Again, thank you very much. This is groundbreaking. This is very important. Thanks for taking the time to share these eye-opening discoveries. And well, I guess we can renew that for the future for another discussion on another exciting topic that Keiichi is working. Keiichi Spiros has been working on many exciting things. So
Thank you.
don't often make
I
it
hope
into
so.
the news, but yeah.
Also, we will follow you to see the developments with Gravity Plus.
Yeah, that's right. Yes, it's
That's
really
right.
exciting. Yes,
That's
it's
right.
the renovating the gravity instrument will be even more powerful. This is really exciting. Yes.
Mhm.
Thank you again. Thank you.